A lot of what we're about to do is going to hinge on the ability to differentiate and integrate a power series. The good news is that when we're talking about power series, a power series to differentiate or integrate requires nothing more than the power rule. Do keep in mind that a power series is, for all intents and purposes, a polynomial of infinite degree. So if we were to talk about how to differentiate a power series, it's much easier to demonstrate what happens on the right-hand side and then explain what happens in the corresponding left-hand side. So with that in mind, derivative of a constant will be 0. Derivative of a constant times x will simply be the constant. Constant times x squared will be 2 times the constant times x to the first power, and so forth and so on. So in every single case, we multiply by whatever the power was and reduce the power by 1. Now to come up with a power series representation of that, that would be the sum of coefficient of 1, coefficient of 2, coefficient of 3, coefficient of 4. That would be n times c sub n times x raised to the n minus 1 power. However, you'll notice that the first term that we have present here is now n equals 1. When we take a derivative, that first term tends to go away due to the fact that it was a constant to begin with. Now, with that in mind, notice what happens if we were to plug in n equals 0. We would have 0 times c sub n times x to the negative 1 power. This starting point isn't actually going to have an impact on anything for now. So you can either leave it as n equals 0 or bump it up to n equals 1, whatever you fancy. You'll notice that the expression that we have inside here is essentially the same as what we had for the power rule as it was brought about. When we differentiate x to the n power, we get n times x to the n minus 1 power. If you take another derivative, this becomes a little bit easier to explain what's going on. On the right-hand side, we would see 2c2 plus 6c3x plus 12c4 x squared, and so forth and so on. The reason that we got this 2, that was 2 times 1. This was 3 times 2, and this was 4 times 3 for multiple applications of the power rule. So if we were to apply the power rule once again here, this would be n times n minus 1 times c sub n times x raised to the n minus 2 power. Now, using the same argument as before, we can say this clearly starts at n equals 2, but there is no harm in having this start at n equals 1 or n equals 0 due to the fact that plugging those numbers in would simply give you a 0 term here. Now, a great question to pose is, what happens to the interval of convergence when we do this? When you take a derivative of a power series, the radius of convergence and the center do not change. So the radius of convergence and the center do not change. The one thing that that does not account for is whether or not it converges at the endpoints. So endpoint convergence can change. What I'd like to do is demonstrate that with our most basic of examples. So the first power series representation that we had was the following. 1 over 1 minus x was the sum from n equals 0 to infinity of x raised to the n power, simply our geometric series. Now with that in mind, the interval of convergence would simply be the open interval from -1 to +1. If I were to take a derivative of both sides, You can either apply the quotient rule here, or think of this as 1 minus x raised to the negative 1 power. I think I'll go with the negative 1 power. Differentiating the negative 1 power will be negative 1 times that quantity to the negative 2 power times the derivative of the inside. That'll be an extra factor of negative 1. Over on this side, you technically have options for what your starting point is. I'm going to call it n equals 1, and we'll do n times x raised to the n minus 1 power. If I were to write out a few terms of this, plugging in n equals 1 would give us 1, then we'd see 2x, 3x squared, 4x cubed, and so forth and so on. This would be the power series representation of the following function. This is 1 over 1 minus x, quantity squared. This will be the sum from n equals 1 to infinity of n times x raised to the n minus 1 power. If you were to find the interval of convergence in this case, you are still allowed to start with the fact that this is going to go from negative 1 to 1, but you would have to recheck the endpoints. Now, I'm already going to tell you that at x equals 1, this thing will definitely not converge, because if I were to plug in x equals 1, this thing right here would become 1 over 0. Therefore, I know it's definitely going to diverge. However, if I were to plug in x equals negative 1, I would have the sum from n equals 1 to infinity of n times negative 1 to the n minus 1 power. This series would be considered 1 minus 2 plus 3 minus 4 plus 5 minus 6. You'll notice that the terms are not getting smaller, the terms are getting bigger. So despite the fact that this is an alternating series, the divergence test lets us know that this will diverge. If you prefer to use the alternating series test, you're more than welcome to do so, but once again, n will not converge to 0 as n goes to infinity. Therefore, the interval of convergence in this case is still going to be the open interval from negative 1 to positive 1.